So let us start. So today we are going to discuss circular motion. So this is also part of our two-dimensional analysis, right? So in the circular motion, what we are going to discuss is what is the angular velocity and what is the angular acceleration and what is the angular displacement. Exactly the same way what we have discussed in case of rectilinear motion. The same thing is adopted to a circular motion where the movement is going to be this particular format. Now actually in a straight line motion, so the particle is trying to move in a straight line motion like this, and where the displacement is treated as a x. So here x is the variable. So it represents the displacement. Now in the circular motion, what happens is, suppose actually if a particle started moving in this particular direction, then actually if you look at from the center of this particular circle, then there will be a change in the angle and there won't be any change in the radius or the distance from this location. Being this is the circle, this distance is maintained constant and the angular displacement is going to be changed. That means the angle is keep on changing as the particle moves on the circle. Right? Now here actually if the particle is moving like this, then actually theta will be the variable. So this is the variable. Here actually the role of x is played by theta in this particular case. Now here actually we have defined the velocity is nothing but rate of change of displacement. Rate of change of displacement is nothing but v is equal to dx by dt. So this is the velocity. Exactly in the similar manner, we are going to define here it is. So rate of change of angular displacement. And this is represented by omega is equal to d theta by dt. So this is the angular displacement. Now here actually we have defined something called acceleration. So acceleration is, and this is the rate of change of velocity. Rate of change of velocity, A is represented as dv by dt. So this is the rate of change of velocity. This can also be treated as d square x by dt square. And this is in the direction of the velocity, right? So velocity, acceleration and displacement in this particular case, as long as all are in the rightward direction, so everything will be in the same direction. Now here, rate of change of angular velocity. So this is usually represented with a letter called alpha, and this alpha is equal to d omega by dt, and this is otherwise written as d square theta by dt square. So this is angular velocity. Now here, so if the acceleration in this particular case is constant, then for rectilinear motion d square x by dt square is equal to a. If a being a constant, we have got all the relations, that is x is equal to ut plus half at square plus initial displacement x naught, and the velocity v can be written as u plus at. So this is the velocity relation as long as the acceleration is constant. Now exactly if we apply the same relation here, the angular displacement theta can be written as, so ut instead of u, so this is omega naught into t plus half alpha t square plus theta naught. So this is the angular displacement at any instant in case of a circular motion with constant angular acceleration. Now the angular velocity at any instant, omega can be written as initial angular velocity plus alpha into t. So this is the angular velocity at any instant. And omega can be written as d theta by dt, and So alpha can be written as d square theta by dt square. So these are the relations actually that we are going to work out with the help of circular motion. So this is actually one-on-one correlation between the rectilinear motion versus the circular motion. So these are the things actually what we have to be talking about in case of circular motion. Now here there is a, suppose if a particle is trying to rotate with a thread, like suppose actually I have tied a thread to a stone and then try to rotate like this. Then actually this particle trying to move in a circular fashion like this. So this circular fashion, when it is moving, there will be a force which is dragging outward, which we call as the centrifugal force. Suppose actually, let us say this is the particle location at one instant where this particle is trying to move in this circular fashion. Then the outward force that is dragging. So this is what we call as, this is centrifugal force. And the tension that is dragging towards the center where we are holding it. So this thread is held by the hand at this location, and there will be a tension that is associated on this particular thread till this point of the circle. Then actually, so this tension is called as the centripetal force. Got it? So this is the centripetal force. So this centripetal force will be always dragging towards the center as long as there is a thread that is tied to this particular particle where it is trying to rotate in the circular fashion like this. Got it? Now actually, in general actually we will try to derive the relation between the displacement and the velocity and the acceleration in any general two-dimensional motion. From there, I will try to bring out the relations of this circular motion, especially related to the centrifugal force or the centripetal force, which is always acting towards the center. First, you note down this. I hope you have understood this concept. Radial and transverse acceleration. Of a particle moving in 2D. Now actually, so a particle actually, let us say this is x-axis and this is y-axis, and the particle is actually trying to move in this particular direction. Now at any instant, if you try to locate the particle which is at this location, and this particle is at a radial distance of r, let us say this is the r vector. So this r actually is the position of the particle, and r represents the position vector of the particle. So this r represents the, at any instant, the position of the particle at that location. And then this is what is also called as the radial direction, because actually anything or any direction which is going away from the fixed point is always called as the radial direction. That means this is a radial direction, this is a radial direction, this is a radial, and this is a radial, and this is also a radial. That means starting from this fixed point, going away in any direction is called the radial direction. And a direction which is perpendicular to the radial direction, that's what is called as the transverse direction. So this is the transverse direction. So this is transverse direction. Don't get confused, this is not a tangential direction. Radial is different and tangential is different. Tangential we mean if I draw a tangent like this, and this is the tangential direction. And the normal direction is a vector which is drawn perpendicular to the tangent. So this is the normal direction. So usually when we wanted to identify the direction of any particular particle, we will try to talk in all these four directions. So that is either maybe radial direction or the transverse direction. Transverse we mean theta direction. Theta is always perpendicular to the radial. Suppose actually this is the angle theta. In polar coordinate system, what we are going to talk about is, suppose if a particle is moving in a circular fashion like this, and this is being the radial, and this is being the theta, and this direction if you treat as the radial direction, and the tangent to that, the perpendicular drawn to the radial direction, which we call as the transverse direction. And transverse direction is nothing but the theta direction. So the increasing direction of theta is called as the transverse direction, which is always perpendicular to the radial direction. But tangential direction is different and the normal direction is different. Here actually you can clearly mention. So this is the radial direction and this is the tangential direction, and this direction which is perpendicular to the radial direction is called as the transverse direction or the theta direction, and which is perpendicular to the tangent is called as the normal direction. Got it? So these are the four different directions actually we are talking about in case of mathematics. Now here, to be particular, we are talking about the polar coordinate system. Hence, we are worrying about only two different directions, that is the radial and the transverse direction. Now, in circular motion, as the path is in a circle, so the radial and the transverse directions are very, very important for us, because we can easily handle the problem with the help of polar coordinate system, where the variables are r and theta. So the components which are in the direction of r and the components which are in the direction of theta, both are important for us, whether it may be velocity or it may be acceleration, right? So keeping that in mind, we are trying to calculate in a two-dimensional motion the radial and transverse directions, accelerations and velocities, right? So for that actually, so this position vector r can be treated as r is equal to r cos theta into I plus r sin theta into j. So this is the position vector. Now here, this is r and cos theta I plus sin theta j. So this is the unit vector. So if you note this magnitude of this vector, so if I call this as r into r cap can be treated as cos theta I plus sin theta j. Now the magnitude of r cap, if you notice, this is cos square theta plus sin square theta under root, this is 1. Hence this is a unit vector in the direction of radius. So unit vector in the direction of radius. So this is the radial direction, right? And the transverse direction is which is perpendicular to that. Now actually r bar can be written as r into, so r cap, where small r is the mod of r. So small r actually mod of r I have treated like this, where this represents simply the magnitude and this represents the unit vector in the direction of the radius. Now the position vector is treated as r bar. Now actually the rate of change of position or the rate of change of position vector will represent the velocity of the particle. So because actually at one point actually this is the position, at another point if I draw one more position vector, let us say this is the another position vector. Now from this position vector to this position vector actually it got changed. That means the rate of change of position vector change is nothing but the velocity of the particle when it is traveling in this particular direction. Now here, so this r derivative you can calculate as dr bar by dt. So you can apply uv here. So r into dr cap by dt plus r cap into dr by dt. So this is the velocity vector which is the dr by dt, and r cap actually from this relation we can write r cap is equal to cos theta into I plus sin theta into j. Now if you take the derivative of that dr cap by dt, why I am taking that is because actually I need that here dr cap by dt. So finally actually I don't want to have any dr cap by dt or any other derivatives except for the magnitudes. I should be having only the directions. So r cap is a unit vector which represents the direction. Now actually the derivative direction, right? So this is actually a little complicated. Rather than that, if I can bring into some factor with some direction. That will be easier for us. For that actually, so r cap equal to d by dt of cos theta I plus sin theta j. So the derivative of cos theta is minus sin theta into d theta by dt into I plus sin theta derivative is cos theta into d theta by dt into j. So this is the derivative, and then this I can further simplify as dr cap by dt is equal to minus sin theta into I plus cos theta into j, and then you can take out d theta by dt. Now if you carefully notice what is happening here, it is minus sin theta I plus cos theta j is the directional part of it, and this is a scalar multiplication, that is d theta by dt is a simple scalar multiplication. Now here minus sin theta I plus cos theta j, this is the vector, and in this vector if you notice sin square minus sin theta whole square plus cos theta whole square is again equal to 1, which essentially means that this is again a unit vector, but we don't know the direction of that. And the direction, if you wanted to identify for that particular vector, then if you try to calculate the dot product of this vector and this r cap vector, so this vector and r cap vector, I dot I cos theta into minus sin theta, and j dot j is sin theta into cos theta. So this is coming out to be 0. So this is a surprise relation where dr cap by dt and r cap, if you find out the dot product, it is coming out to be 0. So r cap dot dr cap by dt is coming out to be 0. So if the dot product is coming out to be 0, we can simply conclude that both the vectors are perpendicular to each other. So this is r cap is perpendicular to dr cap by dt. Now in the definition of the polar coordinate system itself, actually we have given one fundamental decision, that is the r direction and theta direction, which we call as the transverse direction, are perpendicular to each other. That means r cap represents the radial direction, then minus sin theta I plus cos theta j will represent a direction which is perpendicular to the radial direction in the anti-clockwise direction, which essentially means that that is the theta direction. So this direction is, let us say, I call this as theta cap. So theta cap is nothing but minus sin theta I plus cos theta j. Got it? So r cap value actually we have got it, and similarly theta cap value we can write this as minus sin theta I plus cos theta j. So this is the theta cap direction, and this is the r cap direction. So this direction is called as the radial, and this direction is called the transverse. Got it? So these are the two important directions we have got. Now this velocity direction, if you notice, so this is actually containing both the radial and the transverse components of the velocities, because see this r cap getting multiplied by dr by dt, and dr cap by dt involves theta cap into d theta by dt. That means here actually r into d theta by dt is the component of the velocity in the direction of theta cap, because that is the only component of the vector here, and here r cap is the component of the vector, where dr by dt is the magnitude and r cap is the direction, and here r into d theta by dt is the magnitude and theta cap is the direction. Hence from this relation we can make out the velocity in both the directions, one is the radial and another is the transverse direction. Got it? Any questions on this? Any questions on this? So we have got the fundamental relations, that is r cap equal to cos theta I plus sin theta j, and theta cap equal to minus sin theta I plus cos theta j, and dr cap by dt is equal to d theta by dt into theta cap. And similarly, if you d theta cap by dt, because actually we wanted to calculate the derivative of the velocity again where theta cap involves. Hence, as an upfront advantage, I am calculating d theta cap by dt. So from this actually, so if you multiply, so this is minus derivative of sin theta is cos theta into I into d theta by dt plus derivative of cos theta is minus sin theta into d theta by dt into j. So d theta cap by dt minus of cos theta I plus sin theta j d theta by dt. So d theta cap by dt, if you notice, this is again the direction of the r but in the opposite direction of it. That means minus of r cap direction. So minus d theta by dt into r cap. So this is the direction of d theta cap by dt. So dr cap by dt is coming out to be d theta by dt into theta cap, and d theta cap by dt is coming out to be minus d theta by dt into r cap. So these relations actually we are going to use in case of the acceleration. So velocity r is coming out to be r cos theta I plus r sin theta j, and velocity vector is equal to dr by dt is equal to, so r cap, r into dr cap by dt plus r cap into dr by dt, and this can be written as r into dr cap by dt is d theta by dt into theta cap plus dr by dt into r cap. So this is the transverse component of velocity. And this is the radial component of velocity. So this is the radial component of the velocity. So these are the two important components which we have got already. So velocity part is done. Now the acceleration part, so this is dv by dt. This is the acceleration part. So this is the derivative of this. First actually we will do this one. So r cap into d square r by dt square and plus dr by dt into dr cap by dt. So this is one part where I have taken the derivative of this by applying UV rule, and plus the derivative of these three parts actually we have to be calculating. Now d square r, sorry, dr by dt into d theta by dt into theta cap plus r into d square theta by dt square plus into theta cap plus r into d theta by dt into d theta cap by dt. So the derivative actually sequentially goes one after the other. So this is actually for r, it was the derivative, rest of the things no change. And here the second part, that is the derivative, so rest of the things no change. And the third one actually the derivative of theta cap and rest of the values don't change. So this is how actually you have to apply the rule of d by dx of uvw. So this rule actually du by dx into vw plus u into dv by dx into w plus uv into dw by dx. So this is the rule what I have applied now for the multiplication of three different variables simultaneously. So this is how actually you can find out the derivative. Now actually it is time to replace d theta cap by dt with this one and dr cap by dt with this one. So we have to replace and simplify it. First you note down this, we are going to do that. So this acceleration A is equal to, so r cap into d square r by dt square plus dr by dt into d theta by dt into theta cap, because dr cap by dt is d theta by dt into theta cap plus, and here dr by dt into d theta by dt and theta cap plus r into d square theta by dt square into theta cap, and the last one is plus r into d theta by dt, and again d theta cap by dt you can write this as again minus d theta by dt into r cap, so minus d theta by dt into r cap. So if you simplify this, so r cap part you can specify as d square r by dt square minus r into d theta by dt whole square, and this is the r cap part of it, and plus, so dr by dt into d theta by dt, here also dr by dt into d theta by dt, and this is r into d square theta by dt square plus dr by dt into d theta by dt 2 times. This is theta cap direction. So this is the radial component of the acceleration, and this is the transverse component of the acceleration. Got it? Understood? Is this derivation understood or not? So by adapting polar coordinate system for a randomly moving particle, we tried calculating the velocities in the radial direction and the transverse direction. At the same time, the acceleration value in the direction of the radial and the transverse. This is for any randomly moving particle in a plane with the assumption of the polar coordinate system. Right? Now here actually why we are doing this is the same analysis actually we will adapt for the circular motion now. See this, the same thing actually if you try to adapt it, so let us consider one particular case where this is a randomly moving particle. Suppose if the particle moves in a fixed circular fashion. So this is how actually the particle is trying to move. Then actually this is the center of the particle. So this is the center of the circle, and this is the radius of the particle, and this is r. So in a circular motion, if it is moving in a plane which is in the circular fashion, then r is going to be constant. And this value is constant. Now let us take one more assumption. Let us say if the particle is moving with a constant angular acceleration. Let the particle is moving with constant acceleration, constant angular velocity. Then you can write omega equal to constant. It implies that d omega by dt is constant, is 0. So d omega by dt equal to constant, d omega by dt equal to 0 being omega constant. And same thing you can even write as d square theta by dt square is 0, right? So omega being constant, acceleration will be automatically 0, and the same thing d square theta by dt square is coming out to be 0, and r equal to constant, meaning so r equal to constant for a circle, hence there won't be any radial movement. So dr by dt equal to 0, because actually the particle is not moving anywhere further or below the circle. So it is trying to move on the circle itself, hence no change in the radius. So dr by dt is again 0. Now if you replace these values here, so d square r by dt square will automatically 0 because of dr by dt is 0. D square r by dt square equal to 0. If you replace those values, the acceleration is going to be, so 0 minus r d theta by dt whole square r cap plus, so angular acceleration is 0 plus and dr by dt is again 0, theta cap. That means A is coming out to be minus r omega square. This is one very important conclusion. Minus r omega square r cap. R cap is the direction of the movement. So minus r omega square, if you notice, this is what we popularly call as, so this is the centripetal acceleration. The centripetal acceleration meaning there will be a force. As I said earlier, force and acceleration are one and the same always except for a scalar multiplication. So if the acceleration is coming out to be minus r omega square r cap, minus r cap is the direction of the force and magnitude of the force is r omega square. So r omega square is the acceleration which is acted towards the center always. So in a circular fashion, when a particle is trying to move, there has to be a centripetal force which will hold that particular particle in that particular circular path. So in our case, actually earlier when we are tying with a thread and then try to move it, the tension in the thread is going to be the centripetal force, and that is equivalent to minus of r omega square r cap. Right? The same tension, right? It is going to be balanced by the same force in the opposite direction. The tension is equal to this one, and the same thing is even equal to the centrifugal force with the magnitude same, but the direction is opposite to the direction of the centripetal force, which will try to drag the particle outward like this. So r omega square is acted outward, and the tension that is balancing that one, this tension is minus of r omega square. So this is r omega square r cap is the centrifugal force that is acting on a particle when it is moving with a constant angular velocity in a circular path. Got it? So this direction is very crucial. So the centripetal force is towards the center and the centrifugal force is outside the center. So that conclusion we came to this location from this relation, where this will be a master rule where it is applicable to all kinds of the movement, whether it may be a circular or it may be parabolic or maybe it is elliptical or whatever may be the kind of movement of the particle. So this is randomly, you can calculate the radial and transverse acceleration with the help of the vector analysis like this. And from there, for one circular motion where the angular velocity is constant, then this is the only component of acceleration, and that is acting always towards the center. No transverse component of the acceleration, because this is coming out to be 0. Got it? If the particle is moving in the constant acceleration, constant angular velocity. Got it? Suppose if it is not a constant if the particle is not moving with a constant angular velocity, then the centripetal force will also have a component which is in the direction of theta cap as well. That means if the velocity is keep on changing, or if there is an angular acceleration, whether it may be constant or it may be a variable, then two components of the accelerations are going to be there. One is the centripetal acceleration, which is in the towards the radial direction or outside the radial direction. Another is the transverse direction of the component, that is theta cap direction. Got it? The velocity will decide. As long as it is the constant angular velocity, then only you can think of the acceleration always towards the center. Got it? So this velocity magnitude will decide whether it should have the only centripetal acceleration or it can be other component as well. Got it? Any questions on this? Any questions? Okay, you got a fair clarity on this. So the earlier relations, whatever I have written, are for the case where the angular acceleration is not 0. So that is where theta is equal to theta naught plus omega naught into t plus of alpha t square. So that equation is for the case where the angular velocity is not constant. It is keep on changing with an angular acceleration of alpha. In such cases, alpha comes into picture. So here in this case, what I have analyzed is with the angular velocity constant, where the angular acceleration is not there, and there will be only centripetal acceleration which is in the opposite direction of the radial, and that is towards this direction given by r omega square. So Sometimes actually this can also be written as, okay, first you note down this, then. So other relations of angular velocity when it is moving with a constant angular velocity, that is, so d theta by dt equal to omega. So d theta is equal to omega dt and theta is equal to omega t plus theta naught, where if the particle starts at theta equal to 0 at t equal to 0, then theta is going to be omega t. So this is one relation where omega is the angular velocity or angular frequency. This is also called as. So omega is the angular velocity. It is treated in terms of radians per second. So this is omega. So when suppose if this is moving with an angular velocity of omega, then actually in 1 second actually, so it is moving with omega, right? So omega radians per second. Now the arc length, if you try to calculate it, so let us say this particle is moving with a velocity of v. So this is the linear velocity which is moving on the particle, which is moving on the circular path. Now if you wanted to establish the relation between the angular velocity and the linear velocity on the periphery, so the periphery actually the particle is trying to move in this direction, right? So within a time of t, this is covering an angle of theta and this is covering a distance of r theta, where r is the radius of the circle and theta is the angular displacement. R theta is the arc length that it is going to cover. S is equal to r theta, and the rate of change of arc length is nothing but is the velocity on the periphery, which we call as the linear velocity. So linear velocity is the arc length rate of change. So this is usually represented with the letter V is equal to ds by dt, but S can be treated as r theta. So d by dt of r theta and r being constant, r d theta by dt is equal to r omega. So the popular relation V is equal to r omega coming from this relation. From this relation, angular acceleration with constant angular velocity, so we have treated as minus of r omega square is the angular acceleration. So this is the angular acceleration. By magnitude, if you want to calculate it, so this is A is equal to r omega square. This is the angular acceleration. So this acceleration A is equal to r into omega can be treated as V by r whole square. So this is V square by r is the acceleration. So this is the centrifugal or centripetal acceleration. By magnitude, it is equal to V square by r. Got it? So if a particle is trying to move, then force is nothing but force is equal to mass into acceleration. So if a particle of mass m, it is moving on the circular path, then it is subjected to an acceleration of v square by r. So the mass getting multiplied by the acceleration is the centrifugal force or the centripetal force. So towards the center it is the centripetal force and away from the center it is the centrifugal force. So centrifugal force equal to centripetal force by magnitude is equal to mass multiplied by v square by r. So mv square by r is the force, and the same thing is even equal to mr omega square. So both are same. So this is the centripetal force and the same magnitude as centrifugal force. Got it? Understood? Any questions on this? Got it? So this is about the circular motion. Now, circular motion itself is not part of our syllabus, but the applications of circular motion is there, right? So here actually we are going to discuss the constrained motion where the particle is trying to move in a circular fashion. Now in the constrained motion, what we are going to analyze is, suppose if this particle is there, now I have given a velocity to this particular particle by hitting in a tangential direction like this. Now actually we need to identify whether this particle will try to complete the circle, or it will go to this point and come back, or it will go to this point and come back, or actually it completes the complete circle, or it won't move there. So what will be the velocity I should give at this location so that it tries to complete the circle, or it will go to half of the distance and come back. So that kind of analysis we have to do with the help of constrained motion, where the particle is constrained to rotate only in the circular fashion by tying up with a thread. Got it? So in this particular case, how we are going to analyze? So that is all dependent on this angular velocity and the peripheral velocity. All those things actually we are going to use in case of the constrained motion analysis. Got it? Any questions on this? Okay. Okay. Great. So in case of constrained motion, so let us consider a particle moving in a circular fashion by tying up with a thread. So this is the circle. This is the center, and the particle is tied up at this location. Now I have given certain velocity initially at this location on the direction which is tangential to the particle. So this particle actually it is hit by like this. So now actually at one point, if I notice, let us say this is moved to this location. Now we will try to analyze the forces that are acting on this particular particle at any random location. So initially the mass of the particle m will be there. Obviously this mass actually will have certain associated weight which is given by mg, and this is being the thread, and then actually it has to have certain tension which is dragging towards the center always, because actually this is trying to move it like this, then actually it will try to drag away from the center. So the particle trying to move away from the center, but this tension will hold that it won't move in the forward direction like this, it will try to move only in the circular fashion. So this tension is a responsible component for that. Then so there will be a centrifugal force that is acting as mr omega square. So this is the centrifugal force. Now this mg which is acting downwards, and then let us say it is taking an angle of theta with respect to the radial direction, then actually the component of the force along this direction is mg cos theta, and the component of the force which is tangential to the path is mg sin theta. So this mg is going to be divided into two different components. So these two components, one is mg cos theta and mg sin theta. So this tension and mr omega square are balancing out. Now the additional component of the force is mg cos theta. Got it? So this mg cos theta is trying to drag away like this, and tension is dragging outwards, and the particle is trying to move tangential direction in this way. So the particle is moving upward like this, and mg sin theta is trying to drag like this, and tension dragging towards the center, and mg cos theta is dragging towards this direction. Got it? So these are the force components that are acting on this, and this angle. So this is angle theta. This will be same as this angle, because this is a vertical line and this is a vertical line, and this is the r direction. And these components of the forces are actually that are acting on the particle. Now if you give an initial velocity, now actually we have to identify how far it is going to go. If I give a velocity for a lesser value, for a more value, or a medium value, now actually we have to be calculating those things by balancing this equation. Now this particle is moving in this direction. So this direction is called as the increasing direction of S. So increasing direction of the arc length is treated as the positive direction. Then opposite to the S, which is nothing but the decreasing direction of the S, actually we have to treat as negative. So this is S direction, and the angular acceleration or the acceleration in the direction of the increasing S is nothing but d square S by dt square is the acceleration in the increasing direction of the S. And there will be a force, counter force, which is dragging opposite to that. That is minus mg sin theta, which is opposite to S. So by magnitude it is mg sin theta, but it is in the decreasing direction of the S. So yes, hence actually we have to treat this as the negative value. Got it? So this S actually d square S by dt square has to be treated as minus of mg sin theta. Just a minute. Okay. Yeah. So this is d square S by dt square is equal to minus mg sin theta, right? So sorry, and mass times of d square S by dt square, because d square S by dt square is nothing but the acceleration, right? So if you multiply the acceleration with the mass, then actually it is going to give the force, and the same force is getting balanced by mg sin theta in the opposite direction. So m into d square S by dt square is equal to minus mg sin theta, and m will cancel, and d square S by dt square is equal to minus g sin theta. So, and the relation S is equal to r theta, we know this, and ds by dt is the velocity, linear velocity, r d theta by dt. From here actually, d square S by dt square you can calculate as r into d square theta by dt square. So, d square S by dt square you can call as r into d square theta by dt square. So, you can replace it here, r into d square theta by dt square is equal to minus g sin theta. Minus g sin theta. Now actually r into d square theta by dt square. So this one actually we need to solve this differential equation the way we have done in case of simple harmonic motion, where the second order differential equation is solved. Exactly the same methodology we are going to adapt it here. So what I will do is I will try to multiply this equation with 2 times of r d theta by dt on either sides. I will write it here. 2 times of r d theta by dt multiplied by r into d square theta by dt square is equal to minus g sin theta into r d theta by dt, 2 times of. So this one, if you carefully notice, this is r into d theta by dt whole square d by dt of. So this is minus g sin theta into 2r into d theta by dt. So this is actually the derivative of this. So if you take the derivative of it, so 2 times of r into d theta by dt, and the derivative of this is r into d square theta by dt square, r being the constant. So from this relation, this dt and this dt will cancel out, and then you can integrate on either sides. This is being the exact differential. This d and integral will cancel out. R into d theta by dt whole square is equal to minus 2gr integral sin theta. So this is r into d theta by dt whole square is equal to minus 2gr integral sin theta is minus cos theta plus some arbitrary constant A. And then r d theta by dt is nothing but r omega. So r omega whole square is equal to 2gr cos theta plus A. And r omega you can call as the linear velocity v square is equal to 2gr cos theta plus A. So this is the fundamental relation of this moment, right? So v square is equal to 2gr cos theta plus A, and A being the arbitrary constant. Now at theta equal to 0, so this is the location where theta equal to 0, and here actually you have given an initial velocity of u. So that means at theta equal to 0, V is equal to U. So that value, if you substitute in this relation, then U square is equal to 2GR. So U square equal to 2GR plus A, or A is equal to U square minus 2GR. And this value you can put it back. So V square is equal to 2GR. U square minus 2GR plus 2GR cos theta. So this is the relation of velocity and angle theta. So for a certain velocity of whatever you have given it here, so this angle theta and the velocity at any instant, this is going to be related by this relation. Got it? Understood? Or do you have any questions on this? This is a simple derivation. So from the relation of d square s by dt square, which is equal to minus of mg sin theta, and that relation actually is solved for the differential equation, nothing more than that. So this is the fundamental relation. Mass into acceleration is equal to minus mg sin theta. So this is the forward force and this is the backward force, and then we are trying to solve this differential equation by introducing d square s by dt square in terms of theta with the relation of r into d square theta, so with the relation of s equal to r theta, where ds by dt is equal to r into d theta by dt. So from this actually d square s by dt square is equal to r into d square theta by dt square. This is otherwise written as a is equal to r alpha. This is one form where you can write. So where alpha is the angular acceleration and a is the linear acceleration. Now here the same thing actually, once you substitute here r into d square theta by dt square is equal to minus g sin theta. And this relation you multiplied on either side with 2r d theta by dt with the single most reason that you wanted to solve this differential equation. And this differential equation solution you can easily get it by making into the exact form by multiplying this. And this is an integrating factor to solve this exact differential. So by multiplying this, you made this as the exact differential, where d by dt of r d theta by dt whole square will be the exact form of it. On right side minus d sin theta into 2r into d theta by dt. This dt will cancel and this d integral will cancel, and r d theta by dt whole square is equal to integral minus d sin theta into 2r into d theta. So this integral value, once you solve it, r d theta by dt whole square is equal to minus 2gr into integral sin theta is cos theta plus some arbitrary constant a. And this arbitrary constant actually you can solve for it, and that one you can get as v square is equal to u square minus 2gr plus 2gr cos theta will be the final solution. This is the relation for the velocity and the angle theta with the given initial velocity of u. Now there is one more important relation, that is the tension at any instant of this string. So that also we will be able to derive with the same kind of analysis, but applied to this one. Got it? Okay. Now actually you note down this, we are going to derive the relation for the tension as well. So in the radial direction, there are three different forces that are acting on it. One is the centrifugal force, which is away from the center, and the tension towards the center, and mg sin theta, mg cos theta, which is towards the away from the center. That means T minus mg cos theta is equal to mv square by r. So this is the centrifugal force. And this is the tension on the string. And this is the weight component. In radial direction. So these are the three different forces that are acting on the radial direction. Now from this actually T equal to mv square by r plus mg cos theta. So this is the relation. And then v square value we have already calculated. That is m by r into v square is u square minus 2gr plus 2gr cos theta plus mg cos theta. Now from this relation, if you take out m by r, then it is going to be u square minus 2gr plus 2gr cos theta and plus gr cos theta. So this is going to be m by r times of u square minus 2gr plus 3gr cos theta. So this is the relation of tension and the initial velocity and the angle theta. So these are the two important relations when the particle is trying to move in a circular fashion under the constraint of a thread which is dragging towards the center. So with these relations, we will be able to analyze how far this particle is going to move and where the tension becomes zero, where the velocity becomes zero, at what angle actually it is going to happen. All such kind of analysis we can do with the help of this equation, which is equation number 1, and this equation, which is equation number 2. So this is the velocity relation and this is the tension relation. Got it? Understood? Or do you have any questions on this? Any questions on this? Okay, so we'd like to stop the class for today. So the analysis of how far it is going to move and at what height it will come back and what is the condition for the complete rotation, which I am going to do it tomorrow. So I hope no other questions are there. Got it? So till then, good night. Yeah, thank you.